Morning, guys. So far in this chapter here, we started off looking at kinematic equations. We introduced concepts of displacement, velocity, acceleration. We found we had a few formulas on our formula sheet that would interrelate sort of the initial and the final. We saw that initial and final are totally up to us. We can define it using that blindfold on, blindfold off analogy here. We can sort of make calculations from start to finish. The last couple classes have been looking at graphs, so if I don't like this blindfold analogy and I want to see what the motion is sort of in between, a position time graph will plot an object's location as time ticks forwards, or even a velocity time here, plotting the speed at any given time. In yesterday's lesson, we ended off with a little bit of changing from one graph to the other, but basically that's just another way of looking at these motion concepts. In today's lesson here, I'm just going to rehash for you. We know the difference between a scalar and a vector. A scalar is something that only has size or magnitude, just a number to it, whereas a vector, like displacement, like velocity, like acceleration, have direction. They can actually be represented with arrows, and we're actually going to do a quick section here on what's called vector addition, drawing the appropriate arrows for each of the different displacement arrows or velocity arrows, and what we're going to learn is a technique to actually combine one arrow with another arrow. We sort of did this a little bit the very first class when we did the sort of classroom analogy. He can sort of zigzag back and forth, but let's just flesh it out a little bit more in this section here. So for vector addition, we again talked about for a vector. We know vectors here have direction and magnitude. They have both a number and they both have a heading. So what's happening here, again, the direction part is the part that's new for a vector. So let's say I end up traveling to the right. The arrowhead actually tells me the direction, whereas the magnitude, the size, the number of it, is actually given by the size of this arrow here. So if I have a large, if I walk 20 meters instead of 5 meters here, I would expect the arrow would be a little bit bigger than before. As we work into today's lesson here, I'm just going to introduce to you, just for convention, what we use. Again, we're finding ourselves really sloppy in this chapter. Oh, let's just add a negative. Oh, let's just take away a negative. The negative, remember, just implies for you the directions heading in. So for our conventions here, we're going to do two styles of problems. First style of problem here deals with the side view problem. So I want you to imagine you're watching your TV screen or something, and you're watching, like let's say a film, a person walking left to right. In this case here, we can have a coordinate system. In this case, if it's side view, we have our left direction, our going to the right. We have this being up, and we have this down. I'm just going to arbitrarily come and decide here, two of these sides are positive, two of them are negative. I'm going to call the up and the right. I'm going to call those two directions positive, and I'm going to call the left and the down here negative. That's totally by convention. We saw that one time with a gravity question. Well, if my object is only going to fall, why don't I just define down as positive? You can totally do that. But in this case here, it's going to be super important here. We're going to stick to this convention here. What if we switch over to a top view problem? So imagine you got in a helicopter and you're now looking down on the ground, or you're looking down on a map. This time we're going to have our never eat shredded wheat, right? So northeast, southwest. And in a similar fashion, just to keep consistent, I'm going to assume that the upward and the rightward direction, this is positive, north and east, and then the west and south are going to be negative. So in this lesson, we're going to start seeing, oh, hey, this one here is west. Oh, I'm going to add a negative there. Or if out of the math, it comes out as negative. Oh, I remember negative was actually down. So we're actually going to use the positive and negative to interpret direction for us. Once we get that, there is going to be a little work with triangles as well, but you're going to see us sort of haphazardly adding negatives and taking away negatives. So let me just start introducing to you this sort of vector addition question for you. Let's imagine this one here is a top view problem. And let's imagine I'm in a helicopter and I'm looking down at the school. All right. So here's the school. Let's say your journey home takes you, you're going to go 10 meters pure north. And then you need to turn a corner. Let's say it takes you 5 meters pure east. What I'm interested in you calculating for me here is I want you to calculate the displacement. So this is that blindfold on, blindfold off analogy here. I put the blindfold on when you sort of left the school. I know where you began. I'm not watching as you actually do the walk. When you say, oh, I'm home, I'm going to take a look, and I'm just going to figure out here, well, how far have you been displaced? How far are you away from the school, having walked the 10 and the 5? Now, we did this in an earlier lesson here. Well, if I did the scalar form, the scalar, which was distance, the scalar distance was your actual number of steps. You would just say, well, I walk 10, and then I walk 5. So my total distance is 15. I have walked a distance of 15, sure. But again, we saw sometimes displacement, especially when there was actually a change in direction, just because you walk 15, because you turn the corner, you're actually not ending up actually 15 displaced, 15 away from actually your starting point. So my goal here is to find for me here is actually, what is this arrow here? I know you realistically did not do this diagonal, but from blindfold on to blindfold on is my initial condition, blindfold off is my final condition here. I want to say, if you walked in this diagonal, how far away are you actually pushed from the starting school location? What you're going to start seeing here is I've introduced to you a right triangle. This is an easier problem because I have one that's perfectly north, one that's perfectly east. So I'm going to do a right angle here. Well, I've just created this triangle. What if I know the adjacent side and I know the opposite? Could you find the hypotenuse for me? Well, of course. So that's why we did a little bit of practice earlier here. Our Pythagoras would say here, our d squared, which is our hypotenuse, is given by our a squared plus b squared. Right, sorry, d squared. And basically, you just punch in the numbers. And in fact, we're going to use this formula so much so we can actually find our displacement. Maybe I should just say c here, right? So c squared is a squared plus b squared. That's Pythagoras here. Well, your displacement is actually going to equal to the square root of a squared plus b squared. One of my sides, it doesn't matter which you call a or b. One of the sides is 10 squared, the other side is 5 squared. So if you imagine this bottom part for me here, this part does the a squared plus b squared. That would have equal to c squared. This time my c is actually the displacement. I'm just square rooting the sum that you get out of there, and that already gives you your distance. It just helps shortcut your writing a little bit here. Let's go 10 squared plus 5 squared. Underneath the denominator is 125. If you root 125, I get roughly 11.2. So displacement-wise, you have, I know you walk 15 meters. That's almost like the steps that you really took. You really walk north and you really walk east. But because you turn the corner, you actually end up only 11.2 meters displaced, 11.2 meters farther from your starting point. From when I have my blindfold on to when you have your blindfold off, you're only 11.2 meters diagonally away from me. Now that's part of it. So we see that displacement and distance are different. Fine, there was a change of direction. The other part with this directionality is I need to hint to you what the which heading I am. North, east, which way. Now at first you definitely just say northeast. Fine. But what we're going to see in this lesson here is northeast is a little bit too general. Because northeast can be anywhere between the north direction and the eastward direction, right? Northeast can be like northeast this way or northeast this way, right? There's a whole bunch of angles I can actually be going off at. So since I have a triangle, not only can you use Pythagoras to actually figure out how far away you get, what I can actually ask you is I can ask you for this angle. What degrees northeast are you actually going? So that I know you're going to land back home. So in this case here, again, we have a lot of information. We have the 5, the 10, the 11.2. In case I did my Pythagoras wrong, if I can find this angle without using d, I'm going to try it. Well, that would mean I need to do the opposite, and that would be the adjacent. You say to yourself, SOHCAHTOA. For TOA, the tangent of theta is given the opposite over adjacent. And again, we're going to just rearrange that right away. The theta is equal to the shift tan of your opposite over adjacent, right? Second function, sure, get rid of the tan function. And basically what it's saying here is you're just going to punch in, well, the opposite this time is 5, and the other side is 10. Make sure you're in degree mode, right? So arctan or inverse tan here, 5 over 10, this ratio gives me here, give or take, it's 26.6, so let's say 27 degrees. So now we're a little bit better. Northeast could have been anywhere between this quadrant here. Now I have a 27 degree. If you have a picture, no problem. I know exactly which 27 you're talking about. However, we could actually have the picture, what if I went this way, and what if this angle was 27 degrees, right? That would also be a 27, and that would also be in the northeast. How do I pick? No, it's not that one, it's this one here. What we're going to do is we're going to play around a little bit with this writing here. Instead of just saying northeast, what I'm going to use in this section here is I'm going to use a terminology here, east of north. And how this way of writing it works is you're going to look at the second direction. the second direction is going to be the pure direction. So the pure direction is north. If I start from north, and I want you to start aiming, start going 27 degrees east from that pure north direction. So here's pure north, east I know is to the right here. I'm going to start aiming, I'm going to aim 27 degrees east, and therefore I've covered this angle here. If I wanted to describe the other angle, this one here would actually be 27 degrees. This is actually not measured from north. This is actually measured from a pure eastwardly direction. I'm actually going to call that north of east instead. And that would be a totally different angle. Now, just a quick caution for you here. We'll see this in upcoming questions as well. It's possible, especially for multiple choice, when I drew this triangle, I happen to draw the 10 first and then the 5. What you'll end up realizing is if I had gone 5 first and then 10, I would have still gotten the same hypotenuse. I would have still gotten home. But this time, I would have given you this complementary angle, not the 27 like I confused you before, but it's going to be the leftover. If I know the north and east are off by a right angle, if I know this angle here is 27 degrees, I just wanted to remind you, well, the rest of it is sort of 90 minus 27. 90 minus this angle here, give or take, is about 63 degrees. When you're looking for an answer on your like multiple choice section here, maybe it doesn't give you 27 degrees. Well, I'm sure I did it right here. Maybe it's actually written here, 63 degrees north of east. And I'm just going to make a note here. Remember, these are complementary angles that add to 90 degrees. So let me just draw you a quick picture of that here. Between north and east are a 90 degree angle. The answer was 27 degrees this way. I could equally well have pointed that direction if I actually said 63 degrees as well. And again, just notation wise, this is 60 degrees north. You start aiming northward, upwards from the pure east direction, north of east, or the one that we said earlier, east of north. And now we have it completely defined here. What is your displacement? Your displacement is being 11.2 meters away from where you started. It's less than the 15 steps that you actually took. And your angle is 27 degrees east of north or 63 degrees north of east. Right? That's what we mean by vector addition. I took the first vector, that's 10 meters, and then I added it to the other vector here of 5 meters. We're going to make it one step harder now. That one was, in some sense, a little bit easier because it was just pure north. It was just pure east. North has nothing to do with east. Let's do the same scenario here in terms of sort of adding vectors. And what I'm interested in this time, again, I'm in a helicopter, northeast, southwest. Let's say here's my school again. And for another person, they actually happen to walk south. Let's walk south 20 meters. So the first instruction is, let's go 20 meters south. And then they realize maybe there's a park or something. Oh, they can actually cut across here. I want to walk another 35 meters. Right, person lives, well, I guess meters is not that big, but 35 meters. And this time it's going to be at an angle 60 degrees. Let's go east of south. Right? So both of these vectors here individually are easy to do, right? First one here is 20 meters south. So from the school, you end up walking 20 meters south, right? 20 meters. Now you happen to be 20 meters south from there. The other vector happens to be a diagonal. The other one is in the southeasterly direction. So I know it's going to be, for a coordinate system here, it's going to be something like that. For east of south, I start from south as the pure direction. So south is just straight down like this. And I start aiming 60 degrees in the eastern direction. I start going 10 degrees, 20 degrees, 30 degrees, until I get to 60. They're actually marking for you that this is 60 degrees. The length of the arrow is actually 35. I would expect that the length is actually much longer than the other arrow. What I want to be careful here is when you add vectors, just let me write it in words for you here, we always add vectors head to tail. So even though both of these are vectors, right? Vector number 1, 20 meters south. Vector number 2, this 35 meters at this diagonal angle. Even though both of them can be represented with these arrows, I don't add them on my diagram. Well, there's the 20 meters south, and here's the 35 meters east. That would be weird. It's sort of like I walk 20 meters, and then, oh, now pretend you're back at the school, and then now go down. That doesn't make any sense. You are actually down here already. So what we're going to actually do is when we add vectors, I know after the 20 meters, you're actually down here. I'm going to plop a coordinate system. Now what's my next heading? Well, my next heading is I'm going to start going a big triangle, right, 35 meters. And the angle that we said was this one here is going to be 35 degrees. 60 degrees. The length is 35. 35 meters. And when I say add head to tail, well, the head of the blue arrow is added to the tail, the back end of the red arrow. We never add arrows so that they're like sort of like that, right? Oh, the both back ends are connected or both front ends are connected. It's always you did the first one, now from there plot another coordinate system, now do the next one. So this question here is worded very similarly. I want you to calculate the overall displacement. Calculate from blindfold on to blindfold off, how far have I been pushed away from my starting point. So I put the blindfold on, right? You do your walk, you do 20 meters, you do 35 meters at some random angle. When you say, yeah, I'm done, you happen to be standing over here. What I want is I actually want to find the displacement here. So now those of you that are really good at sine law or cosine law, you'll realize you can probably solve it with the information given. The trouble is if I add a third vector, like, oh, you head this way and then you have to turn one more time, then sine law and cosine law are out the window. What I want to do here is I want to introduce to you a technique where it doesn't matter how many vectors that they do, as long as you sort of do this method, it can still calculate for you what the overall displacement is. Just for simplicity, we'll just do 2 vectors at a time. And essentially here, we're going to use the same idea as we did in the first question. First question involved here, if I could somehow create a right triangle, I can just use Pythagoras and get the hypotenuse. I can use tangent to get the angle there. In this case here, in a similar way, let's think of this displacement here as a hypotenuse. Only trouble here is I don't actually have this triangle yet. This south here is perfectly fine, right? That south here gives me part of the lake here, but for this displacement here as hypotenuse, I actually need to know what is what's called the y component of your second vector. When you start heading in this diagonal at 60 degrees, how much ground do you actually cover in the southward direction, and as well have the x direction going in this fashion here. So what I'm going to do here is I didn't actually have this triangle, but I'm constructing this new triangle so that hopefully if I have this big triangle here, I have the 2 legs of the triangle, and that will enable me to do Pythagoras for the displacement and then find the angle this way. So here's our general strategy that works. Okay, we can avoid using sine law, cosine law. The first step here is to break vectors into what are referred to as x and y components. Break them up into the x and y portions. So first vector, let's do this separately here, and then we'll go back to the diagram. First vector, no problem. 20 meters south. If I break it up into x and y, well, let's call it x1. Well, this one here is perfectly south. This is not taking me left or right. So the x1 here is just going to be 0 meters. I don't go any east or west because of this vector here. My vector here, when it travels 20 meters south, is actually taking me on a y1. It's taking me all 20, is taking me in the vertical. And now here I'm going to use my conventions. Because south is the negative direction, I'm going to come along and I'm going to put a negative there. And that negative is just to remind me that negative means downwards. It's more interesting now when I take a diagonal. The part that was problematic here, I don't know when you actually turn to do this diagonal, I don't know how much of this is south, how much of this is east. If you can somehow give me those numbers, I can add the south with the south and I can leave the east just by itself. So diagonals are always problematic here when you want to break up the components. This time my arrow is 35 meters. We happen to have an annoying angle here. This is 60 degrees. Well, that in itself is a right triangle. So let's first break down this triangle here. When I go south and east, it's like going south and then going east. This part here, I'm going to call it y2 and x2. So I'm going to go x2 and y2 here. We can actually figure out from this right triangle from the bottom here, the y2 is actually the adjacent side to the 60 degrees. The x2 is actually the opposite. We can either be thinking in our formula here, well, if I go, let's say sine 60 is opposite of hypotenuse, it's x2 over 35. I want you to get so good at this and just finding, well, because the x is the opposite side and sine does the opposite, effectively the hypotenuse always is brought upwards. So x2 is the hypotenuse sine 60. And without actually doing this algebra here, you should be able to still tell me, well, the y2 is actually the adjacent side, so you can actually find 35 cosine of 60, right? You can try to check it for yourself here. Well, cosine of 60 is adjacent over hypotenuse. Adjacent is y2. Again, we're dividing with 35. You'll notice the hypotenuse comes up in both examples. So I want you to get familiar enough that you can just decide which side is adjacent, which side is opposite. The opposite one will be the sine, the adjacent one will be the cos. No, you cannot memorize x is always sine, y is always cos. Depending on which angle that I give you, sometimes these two swap. So you have to identify for each problem separately. Making sure we're in degree mode again. Let's go 35 sine of 60. 35 sine 60 here is 30.3. 35 cos of 60 gives me here 17.5. So what I'm saying to you here is, I know realistically you actually walk this diagonal, right? You cut across the park and you walk this 35 meters here. What I'm interested in here is, if instead of actually walking this diagonal at the 60 degrees, how far south did you actually get? Just south, okay? Not the whole 35, not the whole diagonal. Well, the y component of it, it actually takes you south only 17.5. That one there is south. I'm going to come along again and I'm going to add a negative just to imply me, well, that one there is south. In the eastward direction, because I'm heading in this diagonal, the eastward component, I know my whole vector is actually 35, but based on this angle here, it actually takes me only 30 meters or so in the east, because east is actually a positive convention. I'm going to leave this as a positive number, no problem. So you can think about it this way here. I don't actually need to walk the diagonal. I can actually think of it, well, first go south, 17.5, and then go east, 30.3, and that'll equally well put you at the same position as you would having done this diagonal. And now looking back at my overall triangle, what we're going to do, pictorially it makes sense then. I took this triangle, the 35 in this diagonal at 60 degrees actually takes me an extra 17.5 meters south. It takes me an extra 30.3 meters east. I now can create my last triangle, right? All this is to try to create a triangle so that I can do Pythagoras again. Now what I can do is I can combine, well, the first vector took me 20. This vector takes me another 17.5. Now I have a total southward direction of 37.5. The eastward direction, first vector didn't take me east at all, so 0. The other component took me 30.3. Now I have the sides of the triangle, and now I'm ready to do Pythagoras again. How I'm going to show this work here is, we now have broke up the x and y components. We're going to add these components. When you're adding components, here's a really big idea. When you're adding components, x and y are independent. Do not add any x values to y values, and don't add any y values to x values. South and north is a totally different dimension as x and y. So here's what I'm doing here. If I try to add up, let's just add up all the x's. So let's take the x1 and let's add the x2. Well, x1 here was 0. I'm not going left or right. I'm not going east or west in that case. It takes me 0. Second vector takes me eastward, so that's a positive, fine. Positive 30.3. So in total, you are 30.3. Again, this is positive, which means east. So pictorially, we had seen this here. The first vector here didn't take you east or west. It's the second vector that actually takes you eastward, 30.3. That's the 30.3 that I got. Now how about the southward? For southward, we're going to add y separately. I'm using the sigma notation. This sigma symbol just means add up or sum. So if I add up the two vectors here, the sum of the y's is y1 plus y2. Here's where it was important to add in those negatives. So I know it's 20. I know from the picture it's 20 and then another 17. I know they're in the same direction. I know it's 37.5. But sometimes you don't always have the triangle with you. Sometimes you just need to look at the numbers here. First vector takes you negative 20. The second vector takes you negative 17.5. If you have added the negatives based on your convention at the breaking components point, you can just simply add these ones here. You don't need to worry, oh, is the y1, are they helping each other? Is it y1 minus y2 or whatever? It's always adding the two vectors. And you notice my answer comes out, in this case here, is negative 37.5. So at least that's consistent. These two help each other. You go 20 and then you go another 37.5. And then we use our convention again. Oh, negative just means south. So now what I can do is I can draw one last triangle. I can draw a triangle that is, so from my school, from the starting point here, I'm actually going a total of negative 37.5. The negative means south, so I pointed south already. I can treat this now as a positive 37.5 because I already have the heading listed here. And I'm going eastward 30.3. So I go eastward. This is 30.3 meters in the east direction. That was positive, so I know to point this way. And now I've created the triangle that I need. The displacement is now given by the Pythagoras, right? The angle is given by tangent. And if you just sort of break it apart, match it up to what you did, the first vector only took you 20 meters. So that didn't really do anything. And then we did a diagonal, which was the other 35 meters here. I've now created a new right triangle where I know the lengths now. I know that total, this is 37.5, and I know it's 30.3 going across. So let's just finish off this question here. The displacement from Pythagoras is the root of the two sides squared. So 37.5 squared plus 30.3 squared, that is Pythagoras. So the root of 37.5 squared added to 30.3 squared. This one here gives me 48.2 meters. 2 or 3 sig figs is fine. That's the size, that's the magnitude. I still need to give you the angle. The angle is the inverse tangent. The opposite is the 30.3 divided by 37.5. Again, making sure you're in degree mode here. 30.3 divided 37.5 gives you here 38.9. So let's say 39 degrees. I know it's southeasterly. I know I end up southeast from where I started. But based on how I defined it, I'm aiming from the pure south direction. And I'm starting to aim 39 degrees in the east direction. So I'm going to call this 39 degrees east of. So just before we practice through another question, on your worksheet, this is sort of worded as a little bit of an aside here. They word it in terms of something called a relative velocity. Now we know velocity sort of means speed, but the relative part is actually, it depends on who we ask. So I'm not going to do a fully worked out example, but let me just give you a feel for what this is talking about. Let's say this is again a top view problem. Let's say we're looking down at a river. And let's say this river here has a current. The current is actually flowing at 10 meters per second. Because this is top view here, this is actually in the eastward direction. Let's say I take my boat. My boat is on this side here. If I happen to know the distance of the river here, let's say the width of it is 100 meters. Relative to me, that I'm sitting on the boat here, maybe I know my boat here. I know the top speed on my boat. Maybe the top speed on my boat here is actually, let's say 50 meters per second. And my goal is to just reach the other side of the river. What I don't know here is if I'm in this boat here, I'm sort of inside. I'm not really like out looking, like actually thinking about the water's current as well. What's going to happen is I'm going to say my boat is just going 50 meters north. However, if you're like us that's sitting in the helicopter looking down at this, we need to say, wait a second. As this boat here is actually traveling upwards, the current itself is constantly being pushing it downwards. So I'm trying to head upwards, it's pushing it downwards. I'm trying to head upwards, it's going to push downwards. Depending on the distance of this river here, I'm actually going to end up, even if I were aiming for a spot directly across from me, I'm going to actually end up at some diagonal. That's going to again be your Pythagoras, that's going to be your hypotenuse. You would need to find for me here, well, how much do I go across? Going across here is 100 meters, going down this side here, depending on the time as well. We give you that lake, we can do Pythagoras to find the rest of it. In some sense, we're both right. In this case here, relative to me, I am only going 50 meters per second. But somehow for us in the helicopter, we see, yeah, I know you're going 50, but you need to factor in that there's a strong current that's actually blowing you downwards. Look at where you ended up. You actually end up slightly east from where you started. We would still do the same component work here. You're going to try to find, in this case, your x1 and y1, right? You're going to try to find those left and right bits so that you can actually do Pythagoras to actually get to that last triangle. So the question I am going to work out with you here is a sample of a vector addition question that has this idea. Instead of a boat that's just simply trying to go across the river, if the person was clever, if they really wanted to be in a spot exactly across from them, they actually may have wanted to aim slightly upstream, and then knowing that as they get slightly pushed upstream, it's the river's current that will slowly push them downwards. That's the only way that they would end up just directly across from them. All right? So let's just work out one other problem just so that you can get a better feel of doing this vector addition stuff here, even introducing this little bit on relative velocity. So here's a question I want to introduce to you here. Let's say I want to add two velocity vectors. So add these velocity vectors. So in that previous example, the boat was going some way, the current was going some way. This time, let's say I have a plane. So I have a plane. Again, I'm going to just emphasize here, this is a top view problem. I'm sitting inside the plane, let's say the windows are shut, and the pilot is just telling me, okay, we are going at 500 meters per second, right? So really, really fast. And my heading here happens to be, let's say 20 degrees. How would you call that angle, by the way? Well, from the pure northward direction here, we're aiming 20 degrees west from the north direction, we would say west of north. That's my first vector. Little do I know here is there's actually a wind that's blowing, right? The wind can be behind me. It can actually help speed me up. It can be a headwind, and it can actually slow me down. This time the wind is just pointing some random direction here. Let's say the wind pushes you in the northeasterly direction. The wind is not blowing that strong. Let's say it's 30 meters per second, right? And this one here also has an angle. And let's say the angle here is, 10 degrees. And again, you can identify for yourself here, well, from the pure easterly direction, we're going to point 10 degrees north from there. So this is 10 degrees north of east is how I would write it. Let's double check here. Again, we are in a helicopter and we're watching this happen. We can see the plane's velocity. We can see the plane's velocity as well as we can see the wind speed. So let me just label these for you here. This is the plane, and then the blue is the wind. You will notice that I followed the rules here. When you're adding vectors, they have to be head to tail. So you see how after I do the plane's velocity here, it's almost like I put a coordinate system again, and I basically have the head of one vector adding to the tip of the other one. In this case here, I'm interested in the overall velocity. So if I'm watching all this happen, I want to know my overall heading. And I want to just emphasize for you here, so this is the total velocity, that's the question mark, that's what I'm interested in. I'm going to try to come up with a triangle that does this as a hypotenuse. At this point here, it's totally a guess. I didn't really take out my protractor to actually measure this 20 degrees, 10 degrees here. Perhaps if I did, maybe this wind here is actually strong enough to actually blow me back actually in the east direction. Maybe I'm still in the west direction, even though it's trying to blow to the east here. We're trying to solve this problem here to try to figure out which heading it is. But in this case here, it's totally a guess. How this one here is a little bit harder than the one before. We don't have one that's in a pure direction. We actually need to break both into components. So first step here, we'll break both vectors into components. I'm going to take the first vector. First vector here was 500 as a hypotenuse. The angle here was 20 degrees. Let's try to find what is a y1 and an x1. So x1 here, relative to this angle of 20 degrees, x is the opposite. So we're going to say x1 is 500 sine of 20, whereas y1 is equal to 500 cos of 20, right? So that's why we practiced our trigonometry early on. 500 sine 20 gives you 171. 500 cos of 20 gives you here 469.8, so let's say 470, right? Sure, this time here is not actually a distance, but velocity is a vector as well. So what I'm saying here is if you go 500 meters per second at this angle, it's sort of like going northward. Well, northward is positive. Northward just 470, positive, meter per second. This time here, x is actually westward. I'm going to come along and I'm going to add a negative just to remind myself that this is actually west. So that later on when I sum up the components, I can take a negative 171 and add the other vector. For the other vector here, now we're going to take the 30 meters per second. It's a smaller arrow because 30 is not all that big. And then what we're going to do is we're going to do just 10 degrees. So for this 10 degrees, again, even though it's a tiny vector, we still need to break up here. Well, what's your x2 and y2? X for horizontal, y for vertical, and 2 just for vector number 2. So x2, you'll notice, based on the angle that I gave you, x this time is actually the adjacent. It's not opposite like the first time, so this is actually the hypotenuse, cosine of 10. y2 is going to be 30 sine of 10. So again, you see, you can't just memorize sine is x, cos is y. It really depends on which angle that they give you. We have that there, so 30 cos 10. This gives me here 29.5. The other one, 30 sine of 10, is 5.2, give or take. I'm going to come along. I need to add any negatives before I sum them together. This time, if I go in the northeasterly direction, it's like going east, sweet, positive. North is also positive, so I can leave those alone. Once you've broken them up, at first, the diagonals were super picky or super hard to add. We'd need protractors and things like that. But now that you've broken them down, just horizontal, just vertical, well, the horizontal parts will just add easily, x1 plus x2, and separately, the vertical parts will just add easily, y1 plus y2. Make sure you've added in any negatives you might need. So in this case here, the first one was west, so negative 171. x2, the wind is not blowing as strong, but it is blowing 29.5. So in total, if I take a negative 171 and I add 29.5, in total your speed is give or take negative 142 or so. So remember earlier we were saying, well, I didn't really use a protractor. I'm totally guessing just based on the size of the number. I think I still go northwest. Now we have it confirmed. If you factor in the plane's horizontal velocity and the wind's horizontal velocity, that takes you a little bit back east, we still end up in the westerly direction. The y's are a little bit simpler. The y's, the plane is going 470. I know realistically it's going 500, but I'm now just looking at the component going upwards. It's like going 470 just straight north. The other y2 here, it takes you, well, just a fraction, 5.2. Just really, really tiny here. I add those two anyways, so 470 plus 5.2 is 475.2. And again, we just look at the convention here. This one came out as a positive number. In the y's, when it's positive, we know it's actually north. And now I've basically done it here. Effectively what we've done, we've broken down the two components. I broke down the horizontal bits here. I took the 171, that would have been because of the plane. I added the 29.5, that would have taken you back a little bit because of the wind. And now what I've done is I've actually calculated for you. Here's a new triangle. From my plane's heading, I'm just going to zoom in for you. From my plane's heading, I actually still go west, but only 142. That negative just implies west. So once you have the direction pointing leftward, we're fine. And then in the northward direction here, the plane's velocity took us 470 upwards. The wind pushes you ever so slightly a little bit higher, the 5.2. So the plane would have been going 470. The wind itself pushes you the extra 5.2. And now I have sort of the combined vector. And now I can say, okay, the total then is actually 475.2. And now what I've done is I've created one final triangle. After doing vector 1 and after the wind pushes you backwards, if I'm sort of outside the plane and I'm watching this happen, I'm watching the wind blow you backwards, I now have I have the two legs of the triangle. I have the 142, I have the 475.2, and now I just need to find this overall heading. What is your final velocity? What is the hypotenuse? And I would also need to give you the angle. Totally possible you could have done the 475.2 first, so going north, and then going this way, and you just get that complementary angle. So leave this for you to finish off here. You should be punching in here. The v is the hypotenuse of this new triangle that I calculated. It's going to be the square root of these two legs that I calculated. 475.2 squared. Very often, I'm just going to take the positive. Well, I thought we went through all this here to get that negative. Remember, the negative just means west, and I already drew the arrow to the west. So it's like saying 142 westerly, so that's 142. So figure out what that velocity is, and we can go theta. Theta is the inverse tan, opposite over adjacent. Again, this is nice. If I sort of got rid of that negative, I already pointed west, so I can just divide the positive number. So try that out for yourself. Do plug it into your calculator as well. Sometimes I get every people show me all the right work. Sorry, this is 142 squared. They show me all the right work, but it's just a problem of calculator work. So this one here is total 496 meter per second. And our angle is inverse tan 475.2 divided by 142. And this gives me here about 73 degrees. How do I name that angle? From the pure easterly direction, it aims the 73 degrees north from there. So north of west, right? So this is sort of a relative velocity problem here. Our plane is truly going 500. It has a heading going northwest, but because the wind is blowing a little bit, it sort of gets rid of a little bit of velocity. Your overall heading is not as northwest as you expected. It's 73 degrees. Earlier, let's just match up here. Earlier we were aiming 20 degrees. Earlier we were aiming about 70 degrees. And now, like we expected, we're pushed back a little bit. And also the wind speed here, part of it is try to blow east. It's actually going to get rid of some of your westerly velocity. The plane realistically was going 500. And now we're over total velocity is actually a little bit less than 500. So practice through some of those worksheets there. Make sure you're good breaking up components. Add the signs based on your convention. And then we create that one last triangle. It's basic Pythagoras and trigonometry afterwards. All right? If you have any questions, just let me know. Thanks, guys.